A quiet industrial decision just flipped the critical metals game on its head. A facility is getting ready to pull gold, tin, gallium, germanium, and then the rare earths out of shredded electronics, not in days, not in hours, but in seconds. And the real story isn't cool tech. The real story is that the metals we're told we'll fight over might already be sitting in our own trash. A process so fast it looks like a lightning strike. So strategic that military planners have reacted with one blunt thought. This could prevent wars. Now watch this. For years we've been trained to believe the only way to get critical minerals is to dig deeper, permit longer, and ship farther. We've been trained to accept a 10-year timeline like it's physics. But physics doesn't care about our excuses. If the feedstock is concentrated and the chemistry is right, the supply chain can be rebuilt in a warehouse footprint. That is what's happening here. Real equipment, real material contracts, real output targets. And it matters because the world is choking on a metals bottleneck. Batteries, chips, sensors, defense hardware, grid upgrades. They don't run on hope. They run on specific atoms. Gallium, germanium, indium, antimony, tantalum, rare earths, the annoying hard-to-source stuff, the stuff that turns into export bans, price spikes, and geopolitical leverage. Let's name the stakes, because critical metals sounds abstract until you connect it to real objects. Gallium is the reason high-frequency chips can run hot without dying. It matters because radar, satellites, 5G gear, and power electronics don't like sloppy heat. Germanium is used in fiber optics, infrared optics, and specialty semiconductors. Why it matters? Modern sensors and secure communications are basically blind without it. Indium sits inside a lot of transparent conductive coatings, those screens and displays we stare at all day. Tantalum stabilizes electronics through capacitors that show up in aerospace, medical devices, and defense gear. Rare earths? They're rare because they're hard to separate, not because they don't exist. And separation is the whole story. So when you hear export restriction, here's what it really means. A factory can have billions in equipment and still stop because it can't get one tiny input that weighs less than a paperclip. That's why these metals become leverage. Because the dependency isn't optional. Now watch the psychology game that gets played on us. They tell us we can't do anything. The supplier controls it. That framing is designed to make us passive, but passivity is a choice. If the bottleneck is separation, and separation can be localized, the leverage can be cut. That is why this process is not just technical. It's strategic. Now zoom back into the flash chamber because this is where how becomes the edge. When you grind up a circuit board, you don't just have metal. You have layers, resins, glass fibers, solder, and components trapped in weird sandwiches. Traditional recovery struggles because the metals are trapped and mixed. Flash changes the geometry. A sudden current pulse tears through the material. The structure collapses. And in that hot, reactive moment, chlorine can grab atoms and form chlorides. Different metals form different chlorides, and those chlorides behave differently. Some become volatile early. Some need more heat. Some can be coaxed out in sequence. That sequence is the business model. Because if you can distill selectively, you can produce separated outputs that buyers actually want, not mixed sludge, real streams. Now, here's the deeper implication most headlines won't touch. If the ore isn't waste, then the most valuable asset isn't a mountain. It's a contract. A guaranteed stream of boards, a guaranteed stream of industrial scrap, a guaranteed stream of tailings, because the flash unit without feedstock is just expensive furniture. The moat is access. So you're going to see a new scramble, not for land, for waste, for data center turnover agreements, for collection networks. That's the next battlefield. Quiet, domestic, contractual. Now, the Prevent Wars line needs adult seriousness. Wars don't start because someone wakes up angry. They start because leaders see a constraint and a temptation. Constraint, we can be cut off. Temptation, we can seize supply. So if you reduce the constraint, you reduce the temptation. You don't make humans angels. You make aggression expensive. You do it by changing supply math. That's why planners care. Logistics wins. Now we keep our feet on the ground. Scalable has two layers. The chemistry can scale and the operation can scale. A factory is discipline, uptime, yield, purity, safety, and customers who pay on time. So the success of this approach will show up in boring metrics. And if those metrics hit, the story gets loud fast. Because every industry that depends on these metals will want a second source, not out of ideology, out of survival. Now, one more point people underestimate. Batteries. They're a metals vault. Cathode metals, anode material, lithium, locked inside products we already bought. If flash separation can pull lithium as a chloride quickly and separate cathode metals efficiently, battery recycling becomes strategic infrastructure. Not someday, now. So here's the cliffhanger. The first metals are the easy test, proof the line can run. But the real prize is the rare earth suite, the stuff that keeps magnets spinning, motors moving, and sensors seeing. When those start coming off the line at consistent purity, that's when the world stops debating possibility and starts fighting over capacity. And the fight won't look like headlines. It'll look like contracts getting locked up, feedstock getting bid up, and the quiet realization that the richest mine in the next decade might not be underground at all. It might be sitting behind a data center waiting to be shredded. So here's the tension we all feel but rarely say out loud. If the future needs more of these metals and the mines take a decade to build, where does the metal come from next year? Not 2035. Next year. That's the open loop. And the answer starts with one ugly truth. Our waste isn't waste. It's an above-ground mine with higher grades than the ground. Let's pause here, because this is the mistake most people make. We assume ore A is rich and junk is diluted. It's backwards. A typical natural ore might have parts per million of a metal. Electronic scrap can have parts per thousand, sometimes parts per hundred. That's not a small difference. That's 1,000 times difference. And when the grade is that high, the economics change. Now the question becomes, can you separate the metals cleanly, cheaply, and fast enough to scale? Because separating metals is the whole game. Mining is just the first chapter. Refining is the war. So what's the trick? Heat. But not furnace heat, not the slow, energy-leaking kind that cooks everything for hours. This is targeted heat. A flash, 2 electrodes, material in the middle, a burst of current. And in under a second, the material rockets to temperatures before it even has time to feel hot. That sounds wasteful, right? Here's the contradiction. It can be efficient because duration matters. Energy is power times time. And time is what this process attacks. But the heat alone isn't the magic. The magic is what's in the air while it flashes. Chlorine. Yeah, that word has baggage. But chemistry isn't about vibes. It's about volatility. At high temperature, many metals react with chlorine to form metal chlorides. And those chlorides often boil at dramatically lower temperatures than the metals or their oxides. Meaning, once you convert the metal into the right chloride, it becomes willing to leave. It evaporates, it distills, it separates itself. Let me make it concrete. Titanium metal, or titanium oxide, can boil near 3,000 degrees IOC, but titanium tetrachloride boils around 136 degrees Celsius. From lava to kettle. Same element, different compound, different boiling point. So if we can convert a mixed scrap into chlorides, we get a menu of boiling points. Turn the temperature, pull one vapor stream, condense it, then turn the dial again, pull the next. If you've ever watched a distillation column separate alcohol from water, it's the same logic, just with strategic metals. And that's why this is disruptive. Because instead of hauling ore to a refinery across an ocean, we can pull metals out where we live, out of discarded circuit boards, out of industrial scrap, out of tailings that were too messy for old technology. So here's our first takeaway. The bottleneck isn't lack of metal, it's lack of separation. If we can separate faster, we can supply faster. And that changes leverage. Now you might be thinking, okay, cool lab demo. But can this run at scale? Can it run every day? This is where it gets interesting. A similar flash method has already been scaled for carbon materials at meaningful volume. That scaling experience matters. It's the difference between a stunt and a factory. And now the approach is being repurposed for metals. The rollout is brutally practical. Start with the easiest, highest value outputs first. Gold, tin, germanium, gallium. Why those? Because they're present in electronics and they create revenue while the harder separations ramp. Gold, especially, is a stabilizer. It's less whippy than many commodity metals, so it can anchor cash flow. And that's important because we're not here to admire chemistry, we're here to measure survivability. Now watch the feedstock. People assume you have to collect phones door to door. No. The real motherlode is institutional, data centers, servers, networking gear. Boards get replaced on a schedule, 1 to 3 years. Mountains of boards, consistent volume. That's what factories crave. Predictable input, predictable output. Now, what about throughput? Early targets talk about processing around 1 ton of printed circuit boards per day, then ramping fast as the line scales. And yes, that's aggressive. But here's why it's plausible. This isn't a chemical bath that has to soak. This is pulses. Flash after flash. Line speed is the point. Second takeaway, this isn't recycling. This is refining, relocated. Now the skeptics ask the right question. Energy. If we're heating to extreme temperatures, isn't this an electricity hog? Key detail, we're not heating a furnace. We're heating the material directly for a blink. And many reactions become exothermic once they start. They release heat, so the system can be less hungry than it looks. There are estimates that the electricity cost per ton can be surprisingly low when the feedstock is rich. Not free, but workable. And there's another twist. Electronics aren't just metal. They're polymers, resins, plastics. When you flash them, those organics can break down into gases, hydrogen and carbon monoxide, basically syngas. Capture it, sell it, or use it to offset power. Stack enough of those efficiencies and you stop being a victim of the grid. This is educational. We manage risk. Now, let's widen the lens, because this is where the prevent wars line stops sounding dramatic and starts sounding rational. Why are critical minerals political? Because supply chains are thin, because processing is concentrated, because export controls weaponize scarcity. When one supplier controls a choke point, every downstream industry negotiates from weakness. Then come the bans, the quotas, the price spikes, the panic buying. And everyone pretends it's normal. It's not normal, it's fragility. So imagine the opposite. Imagine we can take our own scrap stream and pull the same metals domestically. No ocean shipping, no hostage negotiations. Just feedstock in, purified metal out. That doesn't end geopolitics, but it changes the bargaining table. It changes who sweats first. Now here's the next open loop. What happens when the incumbent tries to crush the new method? That's the playbook. Dump supply, crash prices, starve the challenger. So if this metals from trash approach is real, we should expect price warfare, and the defense being discussed is simple. Floor demand. Baseline purchasing guarantees. Not because anyone loves subsidies. Because resilience is worth paying for. That's takeaway 3. The future metals market won't be a pure free market. It will be a strategic market. And don't expect the transition to be polite. If this starts working, incumbents will try to break it. The cheapest weapon is price dumping. Flood the market, crush margins, hope the new plants die young. So watch for governments quietly building guardrails. Baseline purchasing, strategic stockpiles, and buy local rules tied to defense and energy programs. Not because bureaucracy is noble, because dependence is dangerous, and modularity amplifies it. If units can be shipped and installed near tailings ponds or industrial hubs, we can scale like software, copy and paste capacity instead of betting everything on one mega refinery. That's the kind of scaling that changes negotiation power fast. And once buyers taste supply certainty, they rarely go back. The first company to lock a reliable stream of gallium or germanium doesn't just save money, it buys scheduling power, it buys safety. That's how quiet tech becomes strategy. Now, let's get even more uncomfortable. This isn't just about circuit boards, it's about tailings, the leftovers from mining that were not worth it under old tech. Tailings can be messy, but they're massive. And if flash chemistry can separate what old methods couldn't, tailings become a pressure valve, a bridge supply, a way to add metal without opening a new pit. And that's politically powerful because permitting is where projects die. Tailings use the footprint that already exists. That can cut years off timelines. Now watch the domino effect. If the equipment can be modular, skid-based, ship and set, processing moves closer to the waste and the tailings. You're not building one mega refinery. You're building a network, and networks are harder to monopolize. That's a quiet revolution. Decentralized refining. Now, I want you to ask one sharp question. If the metals are sitting in our trash, why are we still shipping e-waste away? Why are we still bearing it? Is it ignorance or inertia? Because once a system makes money, it resists change. And breakthroughs don't spread just because they're true. They spread when they're unavoidable. So what makes this unavoidable? Demand. AI data centers, EV fleets, grid storage, sensors everywhere, defense modernization, and all of it depends on obscure inputs. One missing element, and entire production lines stop. So redundancy gets funded, optionality gets funded, domestic loops get funded. That's what this represents. Not a gadget, a loop. Trash to metal to product to trash again. Now, there's a psychological barrier we have to break. We hear recycled metals and think lower quality. But purity isn't a vibe. Purity is a process outcome. If distillation pulls a specific chloride at a controlled boiling point, purity can be extremely high. A gallium atom from a mine and a gallium atom from a circuit board are identical. We're not gambling, we're measuring. So where are the weak points? Chlorine handling requires discipline, containment, scrubbers, safety culture. Feedstock variability can bite. Boards aren't all identical. Tailings behave differently. Process control matters. But those are solvable problems. Engineering problems, not physics problems. Physics problems kill dreams. Engineering problems get budgets. Now watch the metagame. If a supplier that once dominated processing feels threatened, it can respond with innovation or coercion. More export controls, more restrictions, more national security headlines. So if we see fresh limits on obscure metals, don't be surprised. That can be the reaction to alternatives growing. And the irony is, every new restriction becomes free marketing for independence because nothing says you need a backup, like a supplier threatening the tap. So here's what we do. We watch throughput. We watch which metals come online first. We watch real shipments, not promises. We watch policy. And we stay calm, because volatility is the tax on the impatient. If you want us tracking real-world tech that can flip markets and loosen choke points, hit subscribe. One click, zero fluff. Now, one more thing that changes the shortage narrative. A new mine is a multi-year saga. Exploration, permitting, financing, construction, then ramp up. And sometimes the grade disappoints or politics change. That's why just mine more is a lazy answer. But waste processing is different. The material already exists, already mined, already transported, already concentrated. So the bottleneck shifts from geology to logistics. Can you collect it? Can you shred it? Can you process it safely? Logistics can scale in months, not decades. And that time compression is a weapon, because shortages happen fast. Now let's push the loop forward. This approach doesn't stop at boards and tailings. It points straight at batteries. Cathode metals, anode graphite, lithium, nickel, cobalt. Manganese. If flash separation can pull lithium as a chloride quickly and separate cathode metals efficiently, battery recycling turns from nice idea to strategic infrastructure. Not someday. Now. And if that builds out, the next decade's shortages don't vanish. They soften. Enough to change politics. Enough to change margins. Enough to change who panics first. So I'm going to leave you with 2 questions for the comments, because we build this community by thinking together. First, if the metals we fear losing are sitting in our trash, why are we still acting like we're powerless? Second, would you trust a recycled critical metal supply chain more than a mined one, if it meant fewer choke points and fewer wars? Because if this flash chloride approach scales the way it's being built to scale, the next global scramble won't be for mines. It'll be for waste streams, and that is a different kind of battlefield. Quiet, domestic, fast, and very hard to monopolize. Stay sharp.